So let's start. Today's webinar will be about thermal conductivity and thermal diffusivity. So how one can measure those properties and what are typical applications of that. So more in detail, I will have a look on our products, laser flash, THB, TIM, and HFM. I also want to introduce myself. That is me. My name is Erika. I studied physics, and at Linzais, I'm responsible for the application laboratory with the topics thermal conductivity and thermoelectrics. For those who do not know the company Linzais, you can see a short overview. So the company was founded in 1956 by Dr. Maximilian Linzais in Selb, which is in the northern of Bavaria. In the very beginning, Lindsay started with such data loggers, but focused then later on more onto the thermal analysis. So in SELP, we develop and manufacture our instruments. Furthermore, we have a sales and service location in the US, China, and India, as well as more than 65 distributors worldwide. So that our main business area is the measurement or the construction of measuring instruments for thermal analysis, thermal conductivity, and thermoelectrics. And in South, we also have our own service lab. The company is now led by the son and the grandchildren of Dr. Maximilian Linzais, which are Klaus Linzais, Florian Linzais, and Vincent Linzais. As already introduced a little bit, but now here you see it a little bit more in detail. This is our product range so that it covers the classical thermal analysis like DECs, TGAs, STAs, and dilatometers. We also have instruments for thermomechanical analysis, a quite broad product setup for thermal conductivity and thermal diffusivity determination, as well as thermoelectric material characterization. And we also have instruments for thin film analysis or Hall tests. What is very unique for Linzais is that we offer a high level of customization so that you have, if you have any special requirements, we always try to fulfill them and customize the instruments. Today we will have a look onto the thermal conductivity. What is this property and how to determine that? So that will be the introduction. Later on, we will then have a closer look onto the instruments we provide for thermal conductivity analysis, which are the laser flash analyzer, the transient hot bridge instrument, the TIM tester, and the heat flow meter. After that, I will summarize that and give an outlook in the end for the thin film characterization so that now I will focus more onto bulk materials. In general, heat can be transferred by three main processes, which are radiation, conduction, and convection. Radiation is the emission of electromagnetic waves, and all materials radiate such thermal energy. Convection is a particle or describes a particle stream in heated liquids which carry the thermal energy. Good examples here would be a heater or the Gulf Stream. And then what we will have a look on later on as well is the conduction, so the thermal conduction. Here, no material will be transported so that the propagation of heat will be contributed by phonons, so lattice vibrations, or electrons. So electronic contribution is dominated in metals. With metals, there is also the Wiedemann-Franz law, which is quite helpful when this law relates the thermal conductivity with the electrical conductivity, so that both properties are related via the so-called Lorentz factor L and the temperature, so that if one measures one of these properties, and knows the Lorentz factor and the temperature, one can also find out then the other property. In case of insulators, the phonon contribution dominates here, and in case of semimetals and semiconductors, both parts contribute so that one can detect a phonon and an electronic contribution within the material. And here it's also very temperature dependent, so that maybe within one temperature range, the phonon contribution dominates, and then later on, the electronic contributions will be the more dominating part for the heat conduction. To visualize those three mechanisms, this picture is, in my opinion, very helpful. So we have here a fire where the heat mainly is transported by radiation. On top of that, we have a pot with some water in there. The heat within the water will be distributed mainly by convection, and the handle of the pot will get warm because we have a metal pot, and the heat will be transferred by conduction. So that is a quite good illustration where such heat transfer mechanisms appear. Today we will then focus more on the heat conduction, and the conductivity is quite complex to classify because there's a very broad range of materials with very different thermal conductivities. For example, here on the bottom we have water and oil, so liquid materials, they have a quite low thermal conductivity. Insulation materials have an even lower thermal conductivity, and on the other side we have an extremely high conductivity, for example, with diamond with 2,300 watt per meter Kelvin approximately. So we can see here we have a very, very broad range of thermal conductivities, and also quite of a lot of different materials, metals, insulation materials, liquids, and so on. And these should be covered all in determining the thermal conductivity. So that is not possible with just one instrument typically, so that there are different methods available to cover this complete range. Before we go on, we should have a look onto the two properties, thermal diffusivity and thermal conductivity, as some methods measure only one of that or even both of that, so it's good to know how to distinguish that. So the thermal conductivity is the property which is, the main interest typically, and it's the ability of a material to conduct heat, so thermal energy. Here you can see the relation. So when I have a look onto the heat flow through the sample, I needs to know the geometry of the material, and a temperature gradient should be applied on the sample. The thermal diffusivity is the measure of the ability of the material to conduct thermal energy relative to its ability to store thermal energy. It's closely related to thermal conductivity, and you see here a picture on how to describe that. So, summarizing, a thermal diffusivity is the propagation of a temperature difference. So, one can say that it is how fast the temperature difference is leveled out. You can see here the unit, it's meter squared per second. And the thermal conductivity is how good heat energy is conducted through a material, so the propagation of a heat difference in a material. Both of these properties are closely related, so one can keep this formula in mind where the thermal conductivity is the product of the thermal diffusivity, specific heat capacity, and the density. An important fact is here that all of these properties are temperature dependent, so that for a full analysis, one needs to find out each property at a different temperature. But mainly the thermal diffusivity as well as specific heat capacity show a stronger temperature dependency as the density, which is in most of the cases changing not that significantly with temperature. But why is it so important to know the thermal conductivity? The conductivity is a crucial parameter for the design of a device, especially in regard of heat management. So one needs to know how a material will behave when, it sees some temperature. So that if one does not consider that, it might be that a material can show some failing, with here the example with a crack, because there was just too much thermal stress onto the material. So that it's good to know to simulate that. Also, the thermal conductivity is used for simulations of casting, solidification, and sintering processes, for example. So on the right, you can see an example of different heat treatments onto a material and how that affects the thermal conductivity. So you see here, it starts with 20 watt per meter Kelvin. With a special treatment, one can increase that up to about 45 watt per meter Kelvin. And then one needs to know how the material was treated to find out the thermal conductivity. As a further example, the conductivity can be used for quality control so that the conductivity is tested and will be used as an indicator for the material composition. So there are a lot of different possibilities where the conductivity is used, but I would say it is mainly for simulation processes used for the design of a device, for example. Next, we will move on how to measure the thermal conductivity. The methods can be mainly grouped into two groups. On the one hand, we have transient methods, and on the other hand, we have stationary methods. For the transient methods, the sample is subjected by a thermal disturbance, and the disturbance is observed as a function of time. So that one brings in some heat in the material and has a look on how it propagates through that. For the stationary methods or steady state methods, one applies a temperature gradient through the sample. So, like depicted here, one brings in some heat into the material and has a colder side on the other side. And here one waits until the brought in heat, or yeah, the portion of energy will be the same as the one which will come out. So waiting is a good point here because the stationary methods take typically longer or much longer compared to the transient methods. And this is also depicted here. So for a transient state, one already has a look onto the material when the heat is brought in. Within the steady state, one waits until the system is becoming stable and nothing changes anymore. Well-known transient methods are the laser flash technique, as well as the techniques which all rely on the hot wire technique. As already mentioned, advantages is that the measurement time is quite short. One can cover a very broad thermal conductivity range, and disadvantages here is that the theory for the evaluation is mostly quite complicated. In case of the laser flash, the LFA, the disadvantage is that one cannot determine the thermal conductivity directly, but will get out the thermal diffusivity of the test. For the stationary measurement methods, however, the data evaluation is typically quite easy, and one can directly get the thermal conductivity out of the test. Disadvantages are that one needs to wait until there is a stable state, which might require maybe a couple of minutes or even up to half an hour or 1 hour. The thermal conductivity range is mostly limited, as well as the temperature range is quite limited with the stationary measurement methods. So those methods are realized within our instruments for the thermoconductivity determination. On the left, we see our both instruments which follow some transient technique, so the laser flash analyzer and our THB, the transient hot bridge instrument. And on the right, we see our stationary measurement methods, which are the TIM tester and the heat flow meter, shortly HFM. On this slide, you can see some short illustration where these instruments can be applied to. You can directly see that the THB as well as the laser flash have a very broad range of thermal conductivities, which they can cover so that the full conductivity range is covered here. The THB as well as the laser flash can cover as well a very high temperature range. The LFA, for example, can go up to 2800 degrees. The steady state methods, the heat flow meter and the TIM, are quite narrowed within its measuring range so that the heat flow meter is mainly used for insulation material and the TIM tester for moderately conductive materials. So in the next section, we will have a closer look onto each of these instruments, and we start with the laser flash. The laser flash is a very useful technique as it can cover a lot of different conductivities and a quite broad temperature range. The laser flash setup is a standardized test method according to this ASTM norm for the determination of the thermal diffusivity. For the test, a small and thin specimen is subjected to a high intensity short duration radiant energy pulse, and the energy of the pulse is then absorbed on the front surface of the sample and distributes in there, and the resulting temperature rise at the face is recorded. So this is illustrated here. So we have a power source, which is in our case either a xenon lamp or a laser source. We have the sample and have an infrared detector on the right side of that to collect the signal. A typical signal will look like that. So we have here the temperature rise with time. For the evaluation, the sample thickness is required, as well as the time which is required for the reference temperature rise to reach half of its maximum value, like it is depicted here. So half of the temperature rise, and we get out then the time here. Diffusivity is simplified calculated like that. So we have a factor, we need the sample thickness as well as this half time rise. So you can already see here that firstly the thermal diffusivity is calculated or determined, and if you have information about the specific heat capacity and the density, one can also find out then the thermal conductivity in the end. This measurement method is realized in our instruments like that. So our LFA 500 series uses as a power source a xenon lamp, the LFA 1000 series a laser source. Both of these energy sources are located on the bottom of the instrument, and the beam will be directed to the sample. The sample will be in a sample robot, which can contain up to 3 or 6 or even 80 samples at the same time. The sample robot will be located in a furnace, while we also offer a lot different options to cover in total the range from minus 125 degrees Celsius up to 2800 degrees. And on top of this configuration, so on the same path of beam, there will be a detector located which catches up the infrared radiation emitted by the sample. And the detector will be either a Peltier-cooled one or a liquid nitrogen-cooled one. So typically we use Indian antimony detectors, or for the low temperature range, we use an MCT detector. As already mentioned, we have the sample robot inside the furnace, which can either carry 3 or 6 samples. These are our typical ones. And we also have one for up to 18 samples. Mainly, the device is used for solid samples with such sample holders ranging from diameter 5 to 1 inch, or can be squared with 10 or 20 millimeter as a side length. But we also have some special sample holders. So, for example, one for or for pastes, powders, and liquids, or for some in-plane measurements. The sample preparation is quite simple, so one needs to prepare the sample according to the size of the sample holder. We cover then both of the sides with some graphite spray. This is done to maximize the absorption and emission of the sample. Then this will be covered with a lid to avoid that any light will or laser light will come through the sides directly to the detector. It will be placed here in the sample robot like that, covered as well with a lid to have a homogeneous temperature distribution within the sample container. And then we can close the furnace and do the measurement. Mainly the measurements are done under vacuum, but it would be also possible to do that in inert gases. But the vacuum atmosphere is preferred because within a vacuum atmosphere, the only heat transfer will be done by um, radiation, so that no conduction and convection will happen within the atmosphere. As mentioned before, we find out the thermal diffusivity using this temperature rise with time curve. It is not as simple as just doing it graphically as indicated in some slides before, but for the evaluation, we use some models. And the basic model would be the adiabatic model, describing the heat transfer or heat transport within a material. However, the adiabatic model assumes the ideal case, but in reality, typically this cannot be fulfilled. So there are some corrections which need to be done, which is in the case of the laser flash, mainly the heat loss. So the heat loss from the sample to the sample holder or the surrounding, and as well as some finite pulse length effects appear, especially for fast and thin samples. So that there are a lot of scientists which thought of how to correct this model, this effects, and there are a lot of different models. But mainly the well-known models either consider the heat loss or either consider the finite pulse length. What is unique then for our instrument is that we have this model developed by Dr. Laszlo Dusa, which is the so-called combined model. And this model combines at the same time or considers at the same time the heat loss as well as the finite pulse effects, so that this evaluation model is quite universal and can be used for almost every material, so that it's our default model correcting or evaluating almost every sample we test. So summarizing, the laser flash is a high performance instrument with a lot of different options, measuring the thermal diffusivity of a lot of different materials. And very advantages is that one can also measure up to very high temperatures of 2800 degree, for example. Then the sample carrier will look like that. So that either here 1 or 3 samples can be tested at the same time. Here you see, for example, a furnace which can measure up to 1000 degree. Um, and here on the left, you can see a very special configuration, which was realized for a nuclear application and carries 2 different furnaces. On the right, you can see then a screenshot of our software where you can directly see then also the temperature rise with time, as well as the evaluation. And the software allows you also to select, if needed, a different calculation model. But what can be seen here very good is that the measurement data, which is depicted in blue, and the fit, um, yeah, match very perfectly. So the next instrument we will have a look on is our THB. THB stands for transient hot bridge, and this method was developed in cooperation between the German Meteorological Institute PTB, the Physikalisch-Technische Bundesanstalt in Braunschweig, and yes, the instrument was launched in 2011. The THB allows a fast and easy measurement of the thermal conductivity as well as the thermal diffusivity. With knowledge of density, one can also calculate then the specific heat. There are three different models: the basic, advanced, and ultimate, which each allow different ranges of thermal conductivities. In total, we can cover insulation materials to even very high conductive materials. Also in a quite broad temperature range from -150 to 700 degree, and the samples can be solid, liquid, powder, or pastes. For each application, we have different sensors. So first of all, we have two groups, which are the Kapton sensors and the ceramic ones. The Kapton-based sensors are all based on Kapton foils, where in between some wires are embedded, and these can measure up to 200 degrees Celsius, where the ceramic versions of the sensors are then for the high temperature application up to 700 degrees Celsius. The first sensors which were available with the instrument are the so-called THP sensors. This is also where the instrument got its name from. And these are for quite low conductive materials and can be also used for liquids and powders. But in such a case, we have the metal frame on top because this sensor is very flexible. And for liquids, it's better to have a stable and stiff sensor. For the high thermal conductivities, we use the QSS sensor. QSS stands for quasi-steady state sensor, so that here the measurement time will be a little bit longer, so that we wait until almost a steady state is reached. Then we also have the so-called hot point sensor, which is mainly used for very small samples. So here the tip is about 3 times 3 millimeter, so very small, so that also such small samples can be tested. The other sensors are much larger. So here you see the size of typical samples. So we're in the range of a few tenths of millimeter, so much larger samples compared, for example, to the laser flash. Sample thickness is ranging typically from 3 to 20 millimeter, and for the sample preparation, in case of solids, we need two sample pieces so that the sensor can be sandwiched in between. This means that the sensor needs to be surrounded completely by the material, which needs to be tested. To improve the contact between the sensor and the sample, we compress the complete configuration, for example, with such a sample press or with a weight. In case of liquids and powders, we also need to bring the sensor from both sides into contact with the material. With liquids, it's quite easy. One just takes a beaker and hangs the sensor inside. So also here, as well as with the powders, with our special powder sample container, we use the metal framed sensor to have it more stiff so that it does not bend. Here, just the tip cannot be seen due to the water. But how does the sensor works? The next two slides should explain that. So basically the sensor or all of the sensors are an enhancement of a hot wire technique. The design was just changed so that we have not just one wire, but a very long wire with a meander shape and separated. And in total, within the sensor, there are four of these wires, different distances, and these wires are connected to a bridge. This is also why here this bridge is in the name of the sensor. During the measurement, the sensor serves as a Joule heat source and at the same time as a resistance thermometer. So during the measurement, the sensor emits a constant heating current and also heats itself. So like shown here, so we have the Joule samples, and during the measurement, the hot wire or the sensor will heat up the sample. The temperature rise of the sensor over time is a measure then for the thermal properties of the sample, so the surrounding material. But we do not measure directly this temperature rise, but have a look onto the bridge voltage, which is directly proportional to that, and a typical signal will look like that. So that we will have the bridge voltage, which is rising with time. For the evaluation, we will have a look onto the derivative of that so that we will have a look onto the slope. And the thermal conductivity can be extracted here from this turning point where the slope changes. The thermal diffusivity can be calculated or determined as well based here on this decay of slope then after the maximum. The QSS sensor and the hotpoint sensor work according to the same principle, but the evaluation and the measurement curve just looks different. Here you can see a picture of the software, so it's quite simple design where you can see the sensor type, give some information, see a graph of the test as well as the results. So here you can see then a picture of the THB sensor test so that we will see here on the lower graph the bridge voltage in blue, which is rising, and in black we can see the more or less perfect curve of the derivative of the bridge voltage with the maximum and the decay. On the right, you can see a test of the QSS sensor where it's directly clear that the curve look different. However, the principle of the Joule heat source and resistance thermometer are the same. What we can see here on the upper graph is the bridge voltage, which is rising here. It's the blue curve as well. And we wait a little bit longer until we have here, or yeah, we wait until we have a almost stable state here. And based on this approximation to the stable state, we evaluate in the conductivity. As mentioned before, the THB can cover also a very broad range of temperatures, but the heating needs to be done by an external furnace so that the sensor itself heats up the sample only by a few Kelvin, so that for temperature dependent analysis, we need some furnace. Additional to the sensors, for that we offer a broad accessory setup. So we see here on the top the so-called Peltier controlled furnace for low temperature to, yeah, a little bit or slightly higher than room temperature tests. And yes, it's also possible to perform some pressure control tests with some further tool, as well as we have some sample holders available for liquids and powders. And what we have new here in our product or accessory range here is the so-called single-sided sensor, which requires only one sample piece, so that it's not necessary to sandwich the sensor in between two sample parts, so that it's yeah, quite good to use if one has just some limited amount of sample and or cannot destroy the sample. Furthermore, the sensor sensitivity is mainly um, recommended to use for high conductive materials. As a further comment, which I forgot to tell before, so The system itself is based on a plug and play system so that it's possible to use the same main unit with different kinds of sensors so that one can just unplug one sensor and replug a new type of sensor. So that would be the closer look onto our THB instrument. Now we go further to our stationary measurement methods. First, we start with the TIM tester. TIM stands for thermal interface materials, so that the instrument is mainly used for such thermal interface materials, which are used in power electronics, for example, and cover typically thermal pastes, greases, or pads, so that these TIMs are mainly flexible materials which connect two different materials or two different parts and should close the voids in between those two materials to enhance the contact so that the heat can propagate much better. So, this is often used in computers and electronics to bring the heat apart from the electronic parts so that they do not overheat and fail then later on. So for such materials, the thermal conductivity is relevant as well as the contact resistance to different materials. And for that, we have then our TIM tester, which also functions according to a standardized method, which is the ASTM D5470. Furthermore, it allows some aging studies so that one can do some thermal or mechanical cycling with the material to just check how the material will behave with some time or some heavy use. There are quite a lot of different TIM materials. These can be mainly grouped here into those parts. So type 1 materials are pastes, greases, or phase change materials, for example. Type 2 materials are viscoelastic solids, something, yeah, some flexible material like a pad or tape, foam, and the third group will be then the solid group. And in case of TIMs, these are mainly polymers, metals, or ceramics. As indicated before, the instrument is built according to a standardized method, the ASTM 5470 norm. The norm describes quite detailed how the instrument should be set up. Mainly, we have two plates. We call them meter bars, and these have built inside some temperature sensors, so thermocouples. And for the measurement, the sample will be clamped in between those two meter bars. One of the meter bars, which is in our case the upper one, will be heated and the lower one will be cooled so that we will have a temperature gradient over the sample and thus a heat flux through the sample. To enhance the contact between the material and the meter bars, we also need some contact force as within the THB tests. During the measurement, the so-called thermal impedance is calculated. For that, we need the sample area as well as the heat flux and the temperature gradient over the sample. The thermal impedance is the sum of thermal resistances from the top to the bottom. So the sample's thermal resistance as well as the contact resistances from the sample to the meter bars. Our TIM tester is set up like the following. So we have here those two meter bars with a couple of thermocouples built inside to determine the heat flux. And we also have some cartridge heaters inside the meter bars to just be able to measure at higher sample temperatures. The lower meter bar will be also connected to an external cooling unit so that the heat can be brought away from the material. On the rare side, we have a LVDT built inside to be able to measure directly the sample thickness or control the sample thickness in case of pastes, for example. And on top of the instrument, we have an actuator which can apply some pressure onto the sample. This pressure can be software controlled, so it's also possible to do some pressure dependent tests on different kind of materials. Mainly the instrument is used from room temperature up to 150 and can be used for materials with a thermoconductivity range of zero point 0.1 to 50 watt per meter Kelvin, but mainly the thermal interface materials go up to 20 watt per meter Kelvin, so that the upper limit can be used for some further materials. Also, the meter bars, as well as the temperature range, can be customized a little bit so that the temperature range can be also extended to lower temperatures as well as high temperatures up to 300 degrees Celsius. The meter bars can be selected either in round or square, typically with the size 25 or 40 millimeter. There are also different meter bar materials which can be used for different applications. Before setting up such a TIM tester, one needs to know which method or which size of sample is the most convenient to prepare, because the sample needs to have the same size as the meter bar. So that this size should be thought of before selecting the meter bar geometry. The contact force can be also changed. So mainly we use the 1 kilonewton actuator. The pressure onto the material will be realized then according to which geometry the meter bar has. And the contact force can be extended up to 5 kilonewton. You can see here on the right the picture of this customized instrument with a 5 kilonewton actuator so that it will look a little bit different to the standard setup. Mainly the samples are constructed in such way that the thicknesses are between zero point 0.1 to 5 millimeter. In general, the system can measure samples up to 10 millimeter. This mentioned ASTM norm does not only describe on how the instrument should be set up, but also determines how the measurement should be done as well as the evaluation. For determining the thermal conductivity of a material, it is necessary to test the thermal impedance of 3 different sample thicknesses. As the system will firstly measure the thermal impedance, which still has the influence of the contact resistance between the material and the meter bars, there should be a method on how to subtract this contact resistance. And that is done by linear regression, so that we test different sample thicknesses where the variation will be the thermal resistance of the material, but the contact to the meter bars will be still the same, so that we will get in the end a linear relation like that. And out of this curve, we can find out the apparent thermal conductivity of the material, which is the inverse of the slope. And the offset of the curve will correspond then to the contact resistance between the material and the meter bars. So that is how the measurement principle works. For solids, the easiest would be to just prepare 3 different samples with different thickness. It's also possible to stack several samples on top of each other when there's only one sample thickness available. In case of pastes, for example, one just applies the paste onto the meter bar and compresses it step by step using some pressure with the actuator. here you can see a screenshot of the software. So first of all, there's a window on how to set up the measurement, giving some information, giving the different sample thicknesses and contact pressures or the different distances for the paste measurement. It's also possible to define a temperature profile as well as the gradient over the sample. During the test, one will see in live the different values, how they will change with time. As soon as this test is done, a report will be generated and will look like here on this slide. It will show then the general information as well as the individual steps. So here you can see a test of our festival reference material performed at 50-degree sample temperature with 20-degree gradient over the sample. Thicknesses were 1.5, and 2 millimeter with a contact pressure of 1 megapascal. And these are the thermal impedances determined during the test. And the effective thermal conductivity is calculated as well, which is basically just the sample thickness divided by the thermal impedance. But here you can directly see that this effective thermal conductivity varies. This is just due to the fact that here this effective thermal conductivity still includes the contact resistance, so that one should have rather a look here onto the bottom of the report where the conductivity is determined out of the inverse of the slope of the relation between the impedance and the sample thickness. So this is all done in the software, and one also will see then the contact resistance. A similar measurement technique and setup uses our heat flow meter. The heat flow meter is also a stationary measurement method using two plates where the sample will be sandwiched in between. One of the plates will be cooled and the other one will be heated to generate a temperature gradient and generate a heat flux through the sample. This heat flow meter is also designed according to some norms, so it fulfills different norms, ASTM and ISO norms or DIN norms. And as told before, the instrument is mainly used for insulation materials or building materials. Here, size typically does not matter, so that typical sample sizes are in centimeter range, like with the HFM 300. The samples will be 30 times 30 centimeter, and thicknesses range up to 10 centimeter. You can also see here from typical thermal conductivity range that we move in the very low range of conductivity. So the system also uses the method of two plates. So here's the illustration of that. We have the hot plate and the cold plate, as well as the test sample in between. Between the sample and the plate, there's a heat flux transducer each, so above and below the sample, to determine then the heat flux through the sample. Out of the measurement, we can calculate the so-called heat transfer coefficient, or also well known as the U value. This value is often used in the building industry or insulation material industry to be able to compare different materials. We can also calculate out of the heat flux and the sample geometry the thermal conductivity as well as the thermal resistance of the material. As mentioned before, the steady state measurement methods take quite a while, so that with the heat flow meter, mainly tests are done within half an hour or 1 hour at one temperature. Laser flash measurement, for example, at one temperature, one shot takes mainly about 1 second, so that it's much faster compared to this steady state measuring methods. So now we had a closer look onto the different instruments we offer for bulk materials. So quickly summarized, we have the laser flash. It's a quite universal instrument and can test insulation materials up to very high conductive specimens, and it determines mainly the thermal diffusivity in a very broad temperature range, can be used for solids, liquids, powders, uses quite small test samples, whereas the also transient technique, the THB, which is also quite universal, so that one can test also insulation materials up to high conductive samples. Temperature range is a little bit more limited here, but it also allows the test of solids, liquids, pastes, and powders. Sample dimension is higher compared to the laser flash, but it's still not that large. In the same order of magnitude of sample size, the TIM tester works, which is a steady state measuring method for determining the thermal conductivity of moderate thermoconductive materials, so mainly these thermal interface materials like pastes, pads, or solids. Because of the application field, also the temperature range is not that large, and um, thickness and size range is in the lower millimeter, a few tenths of millimeter range. The heat flow meter uses very large samples, which are mainly in the centimeter range. The thermoconductivity range is very low, so that it's mainly used for insulation materials or building materials. Because of this application, also this temperature range was designed for, so also a moderate or moderate temperature range. The big question is now how to decide which instrument can be used for a specific application. This is often not that easy because in the very beginning, different instruments can be used for, and then one needs to step by step figure out the conditions to focus on just one instrument. So the choice of the measuring method depends very strongly on the application. So that in the beginning, one needs to find out the following information. So which type of material should be tested? Is it solid, liquid? Is it a powder? Can it be compressed? Has it a homogeneous or an inhomogeneous structure? What is the surface roughness? And so on. Next would be to figure out the thermoconductivity range. So if one has very high conductive materials, mainly the laser flash and THB only can be used. Also, the temperature range limits the selection of the instrument for very high temperatures. So let's say starting from 300, 400 degrees Celsius, mainly only the laser flash can be used. For room temperature or close to room temperature applications, one can think about the THB or TIM tester mainly. And furthermore, the size and the thickness of the material can also influence the choice of instrument. So if one just has a very small amount of sample available, it's also mainly the laser flash. For very large samples, which cannot be cut or treated any more further, then a THB will be the choice of instrument. And then, of course, one needs to think about some further measurement conditions. So the atmosphere, if one needs to apply some pressure onto the sample, and so on. So the here shown points are the information which are necessary to be able to decide which measurement method will be the right one for the specific application. And on our website, we have a first rough guide on how to determine the correct test method. So you can see here a screenshot of that. So you can see the LFA, TIM tester, THB, and HFM. as well as the thin film characterizations, but I will just do not focus on that right now. So first of all, one needs to think about which properties of interest, then the temperature range, and the type of material. Here you can see that indicated with the smileys here in green, orange, and gray, which measurement method is very good suited or can be used, but it's not that ideal, um, to just get a rough overview on what can be used. So in this webinar, I focused mainly on the investigation of bulk materials, so solids, liquids, powders, and pastes. But a huge trend is to uh, get instruments and parts smaller, so the miniaturization of materials, so that thin films are becoming more and more of interest. The production of thin films is quite complex, and also the characterization of thin films is more complex compared to bulk materials. But it's important to test also thin films, and not just rely on the data of the bulk material, because it might happen that the physical properties of thin films differ from bulk material. This is often due to some parasitic surface effects, which are much stronger due to the smaller dimension. And the thin films have also a have high aspect ratios, um, which need to be considered and can influence the physical properties. So mainly the characterization is very important for semiconducting industries, but there are also many more different applications where these thin films are used for. Due to the scale of the sample, we need some other measurement techniques, which are typically more complex. And these approaches we offer in our product range will be handled separately in a further webinar, which will be in 2 weeks. So here the measurement methods, PLH, which stands for periodic laser heating, the FGTR method, the frequency domain thermoreflectance test, you see here a typical sample of that, and the thin film analyzer, which uses such chips where the sample will be deposited on, will be explained in more detail. So as mentioned, this webinar will be in about 2 weeks, or it will be in 2 weeks. So it will take place on the 24th and the 26th of October. And my colleague Sebastian Vollner will there explain you these thin film techniques for testing the thermoconductivity more in detail. So I now reached the end of the presentation. I want to thank you very much for your attention.